You are lowering a bucket into a well. When the bucket is 4 meters above the water, your hand slips, and the bucket falls towards the water while unwinding the spindle. What is the speed of the bucket when it reaches the water? This problem is amenable to both force methods and energy methods. If it had been a force problem, you would be asked for the tension in the string and the acceleration of the bucket. However, since we have instead been asked what is the speed of the bucket or velocity after having moved a certain distance, we're led to consider this by energy methods because the speed will come from the kinetic energy term and the height will be involved in the potential energy term. The manner by which we solve any energy problem is to identify the appropriate moments and then connect them via energy equations. In this case, we will identify moment 1 as the moment when you release the handle on the bucket, and moment 2 as the moment just before the bucket hits the water. We'll be connecting moment 1 to moment 2 using energy methods, and the first question we ask for energy methods is whether there is any work due to a non-conservative force. In this case, we see that there is not work due to a non-conservative force, so that work non-conservative is 0, and this means the technique by which we will solve the problem will be conservation of energy. When energy is conserved, this implies that the energy at one moment, call it moment 1, is exactly the same amount as the total energy at another moment, which we'll call 2. To generate the necessary question, we have to ask ourselves 4 questions at each moment. Let's begin with moment 1. At moment 1, do we have translational kinetic energy? The answer is no, because the bucket is not yet moving. At moment 1, do we have rotational kinetic energy? The answer is also no, since the spindle is not yet turning. However, at moment 1, we may have gravitational potential energy. The answer as to whether we do depends upon where we assign y equals 0 in the problem. Since it's simplest to define y equals 0 at the lowest point in the motion, we'll do so at the moment where the bucket hits the water, known as moment 2, and so this means that indeed at moment 1 we do have gravitational potential energy. It is the bucket that has the potential energy, and so the gravity term is mass times g times the y at moment 1, which is 4 meters. At moment 1, we also ask about spring potential energy. There are no springs in the problem, and so this is the total energy at moment 1. To conserve energy, we need to set this total equal to the amount at moment 2. We ask ourselves at moment 2, do we have translational kinetic energy? And the answer is yes, indeed we do. We do because the 2 kilogram bucket is moving downward at this moment. So that's 1/2 mass times the velocity at moment 2 squared. We also ask ourselves whether we have rotational kinetic energy at this moment. Indeed we do. We have this because the spindle is turning. This gives us a 1/2 I times omega 2 squared term. At this moment we have no gravity potential energy, and also there is no spring. The 2 terms that we wish to eliminate in this equation are the moment of inertia and the angular velocity omega subscript 2. We recognize that since the spindle can be treated as a solid cylinder, its moment of inertia will be 1/2 its mass, which is 0.8 kilograms, times the radius of the spindle squared. We're not given the radius, and so we hope that a cancellation comes along. Omega at moment 2 can be related to the velocity by recognizing that the string unwinds. In this case, the linear velocity of the bucket is directly related to the omega of the spindle via the relation omega 2 is v2 divided by the radius of the spindle. Gathering all these terms yields the following equation. Notice that we've been very careful. The term for the rotational kinetic energy is 1/2 I omega squared. The moment of inertia is 1/2 mr squared. This leads to two 1/2 factors in order to get that term correct. Just as we had hoped, the radii will cancel. 0.8 over 4 is 0.2, so that the right-hand side simplifies to 1.2 times velocity 2 squared. And plugging in the numbers, we find a velocity of 8.08 meter per second.